Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. In the previous video, we have talked about the spin-orbit interactions and about the Hund's rule. Let's take forward the discussion and understand the LS and JJ coupling. The LS coupling is also known as the Russell-Saunders coupling. It is namely the spin-orbit interaction. Now consider the case of low atomic number atoms for which the value of Z is very low. And as the spin-orbit interaction energy is proportional to Z raised to power 4, the interaction energy can be considered as a small perturbation. And the main energy is given by electrostatic interactions. Now, according to the Hund's rule, the electrostatic interactions controls the value of L and S. Now, the electrostatic interaction combined L and S separately for electrons. And only then the spin-orbit interaction act as a small perturbation. Which splits each term into fine structure levels labeled by J. So therefore, at the first step, all the L values will add up to give the total orbital angular momentum L, and the all S values for different electrons will add up to give the total spin angular momentum. And this will be due to the electrostatic interaction, which will be the dominant term in this particular case. And after this, the total angular momentum J is given by L plus S, which will be due to the spin-orbit interaction, which is a small perturbation in this case. Now let us consider the other case, that is for high atomic numbers. For these, the LS coupling will not work, as the spin-orbit interaction cannot be treated as a small perturbation. So a better scheme is JJ coupling, so that the Hamiltonian in this case will be equal to Hamiltonian due to spin-orbit interaction plus the Hamiltonian due to electrostatic interactions. Here the dominant term will be the spin-orbit interaction, while the electrostatic repulsion will act as a perturbation, so that the dominant spin-orbit interaction will couple the spin and orbital angular momentum of each electron to give the total angular momentum for each electron as Ji, and consequently a weaker electrostatic effect then couples the total angular momentum from each electron as summation over Ji equal to J. This type of coupling is known as JJ coupling. Now let us take an example to understand the JJ and LS coupling better. For that, consider carbon and lead, which both are group 14 elements, therefore having 4 valence electrons. The electronic configuration for carbon is given by, and for lead is given by. So therefore they both have 2 p electrons in their outer shell. But as Pb is much further down in the periodic table than the carbon, so therefore In case of carbon, we will use LS coupling, while in case of lead, we will use JJ coupling. So therefore, for carbon, we can use Hund's rule as there are two electrons. So therefore, we need to arrange these two electrons in order to maximize L and maximize S. So therefore, in this case, the value of S will be 2 times half, which will be equal to 1, and the value of L will be 1 plus 0, which is again 1. Now as the shell is less than half filled, so therefore J must be L minus S, which will be equal to 0. So therefore the term symbol for ground state will be 3p0. Now for lead, the spin orbit interaction is the dominant energy, and it is more appropriate to use JJ coupling. Now as here we have two electrons, both with S values as half and L values as 1, so the combination J can be half or 3 by 2, depending on the sign of spin orbit energy. Now it turns out that this actually leads J equal to half. So therefore both electrons will have J values equal to half. And these can couple via weaker electrostatic effects to make the resultant J as 0 or 1, where J equal to 0 is the ground state because of the Pauli's exclusion principle, as the electron must be kept apart in the antisymmetric state. So therefore the good quantum number in this case is J1 equal to J2 equal to half, or J is equal to 0. Therefore L and S are not good quantum number in this case. Now let's move on to our next topic, that will be nuclear spins. It is not only the electrons in an atom which have a magnetic moment. The nucleus often has a non-zero spin resulting from the angular momentum of the nucleus. For each nucleus, there is a quantum number I, called it as the nuclear spin quantum number, which represents the total angular momentum of the nucleus. Here I can take values as 0, half, 1, 3 by 2 and 2 and so on. And the z component of angular momentum takes values mi, which runs from minus I to plus I. The magnetic moment for nucleus is given by mu is equal to gi mu n times I, where gi is the nuclear g factor and mu n is the nuclear magneton, and its value is EH cut divided by 2 times mass of proton, which will be equal to 5.05 into 10 raised to power minus 27 ampere meter square, which is typically 1,000 times smaller than the Bohr magneton. Normally we ignore the nuclear magnetism. However, we can detect it using a very sensitive resonance technique known as nuclear magnetic resonance. Now let's move on to next topic, that is hyperfine structure. Inside an atom, the nuclear moments can magnetically interact with the electronic moments but only very weakly. This leads to energy splitting, which are even smaller than the fine structure and is known as hyperfine structure. This weak interaction between nucleus and electron is known as hyperfine interaction. Consider the nuclear magnetic moment sits in the magnetic field produced by the motion and spin of all electrons. So this gives the energy term as minus mu dot b electrons. Now this b electrons is expected to be proportional to the total angular momentum of all electrons, that is J. So the Hamiltonian for the hyperfine interaction can be given by A I dot J. Here A is the parameter which can be determined experimentally, and it measures the strength of the hyperfine interaction. The precise form of the hyperfine interaction is complicated for a general atom, but can be worked out in detail for a single electron atom interacting with a point nucleus. Here, the total angular momentum F of the atom is given by the combination of nuclear and electron as J plus I. Here, the quantum number F can take values from J minus I mod to J plus I. Here also, F square is equal to J square plus I square plus 2 times J dot I. So therefore, the expectation value of A I dot J will be equal to A by 2 into F plus 1 minus I into I plus 1 minus J into J plus 1. The hyperfine interaction can be added as a perturbation, and it splits the electronic levels into different hyperfine structure levels labeled by F with degeneracy of 2F plus 1, so that these states can be split up into different MF values by applying a magnetic field. Here also the splitting of different hyperfine structure levels follows the Landes interval rule, as the difference in the energy levels of F and F minus 1 will be proportional to F. Now let us take an example to understand hyperfine structure. Consider the example of atomic hydrogen in the ground state, which contains one proton. So therefore I will be equal to half, and there is only one electron. So the value of J is equal to the value of S, and it will be equal to half. So therefore the value of F will be equal to from I minus J to I plus J. So therefore we have two possibilities as 0 or 1, so that the state with J equal to half and I equal to half will split into F equal to 1 and F equal to 0 with energies as minus 3A by 4 and A by 4, and the difference between the energy levels will be equal to A. The energy splitting between these states is extremely small, about 6 orders of magnitude smaller than the typical electronic energies, and it corresponds to the electromagnetic frequencies of about 1420 MHz or a wavelength of 21 centimeter. Here each F value have the degeneracy of 2F plus 1, so F equal to 1 can split in 3 levels as MF value equal to 1, 0 and minus 1, and the ground state will only have MF equal to 0. Let's end this topic here, and in the next video we will talk about adiabatic demagnetization. Thank you so much for watching this video.